Today we have 8.4 and 11.1. 8.4 is where we're starting, so if you're going to tie our notes. What we have here is a really pretty brief topic that I think we can do probably in about 20 minutes, and then we'll look at 11.1. We'll probably finish 11.1 today, which means we're on track to probably finish chapter 11 next week. So really only sections 2 and 3 left after this. So 11.1 is also partial review from parametrics. So anyway, hope the tests are done, submitted, all of that. But so this 8.4, you can title your notes, length of a curve. Length of a curve. So I have a function here, the sine of x, and I am interested in how long the curve is between 2 points. Okay, and so we're really thinking about, like, if I'd lay a piece of string along this curve, like how far is it from here to here? Now, I've constructed a triangle there, and I hope that this is starting to conjure up some thoughts of some things that we've done before. Like, notice that the hypotenuse of the triangle is not the length of the curve, but it could be an approximation of the length of the curve, right? How would I get a better approximation for the length of the curve? Sum up an infinite number of triangles. How long should the base be for those triangles? Yes, how long should that change in x be? If I want very little, give me a better answer. The limit as it's approaching 0. So notice that this is a lot like a notion of locally linear then, right? So if I squeeze it down, if delta x is squeezed down, the hypotenuse gets closer to the curve. So I have some work here. I'm going to try to develop a formula then, because the formula has to be based then on Pythagorean theorem in some ways, right? We're going to end up seeing an integral with some notion of a Pythagorean theorem here as well. So the first observation is I'm going to say this, like, you don't have to write all of these steps down if you just want to kind of think about it, and then we'll get the formula down. So making sense of what I'm writing. So notice I'm saying L is about that root. And notice that is the Pythagorean theorem, right? The hypotenuse squared is the sum of the legs squared. And I'm just solving that, but not equal to. Because L really is this length. So maybe I'll mark it here just for our drawing. Like, I'm going to call that length L. So the hypotenuse is about L. And this is exactly what you just said, that if I could sum them up as delta x is approaching 0. So I want to try to write that in symbols. So I'm going to have a sigma of that. Still with me? But I could rewrite it that way. So how would you characterize what I did? Like, if you're okay with the top line, what did I do to get to the bottom? Which is reverse distributive property is factoring, right? So factor out a delta x squared. That's what we would get. You good with that step? Right? Or multiply it back out. Don't we go back here? Right? So, okay. So if this is true, if I need to sum up all of those, it'd be the same as summing all of these up. But I really want it to look like some kind of integral, don't I? Right? Like, I'm really wanting delta x to be 0. There really is some limit as delta x is approaching 0. It's some infinite sum that I'm trying to do here. So I'm going to make another manipulation that That's a simple justification. Why is that statement true if the one above it's true? By properties of square roots is exactly what I would have said. So that's just simplifying that. Notice delta x here, like it's some positive number, isn't it? Right? It's some thickness of, or it's some leg, I should say, of the triangle. Right? So this is a positive number, so the square root of that thing squared is that thing. Do you see it? What is the integral then? What is the integral that's going to give the length of the curve? So remember that the integral is the combination of the limit and the summation symbols, right? So that's the integral symbol, has these pieces in it. Delta x is the thing that's going to 0. And I have a delta x sitting right here. What do you think that is for the integral? Dx, right? Isn't that exactly the thought we've had for months now, that dx is the change in x, it's the width of the rectangle, all those things. So this piece ends up being dx over here. Well, this is some square root, but I want to look at this because you actually have a much better name for that. Now, when you just look at that yellow portion, if I said, what is it? There's a good Algebra 1 answer. It's slope. But is it slope of a secant line? Because that's actually what we have here, right? If I think about delta y divided by delta x, wouldn't it be the slope of that secant line that's connecting those 2 points? Secant, remember, cuts through the shape. Is this a secant line that we're talking about a slope for? It's a tangent line. So tell me the symbol that corresponds to slope if it's the tangent. What am I going to write? dy dx. So notice it's dy dx squared. So actually, there's the answer. There is the length of a curve between two x values. It's the integral from a to b, well, the values that we're trying to find the length for. And this piece, where's this 1 come from? Why is this a plus and why is that squared? You should say all of this is from the Pythagorean theorem. That's all it is. We're finding the hypotenuse, and this 1 came from factoring it out, so we can get a dx over there. That's it, done. Okay. So here's the question I'm going to ask. Do you have this written down? I can put it on the other screen, but if you have it, it'll be easier. You are good students, so you wrote it down. Okay. So suppose I would like to have a sheet of metal. So think like a corrugated piece of steel that is in this kind of pattern, right? Do you know what I mean by corrugated? You've seen it like on old roofs and things, like garages or sheds, like galvanized steel. Like it's got this curve to it. What if I want the pattern here to be sine of x? And I want the total width to be 4 feet. So my question is, what length of steel would be required to finish with a piece that's 4 feet long? Answer that question at your table. What? Yeah, what's its length? This dimension, we can make it probably whatever we want, so I'm not really worried about that. But if I want the distance across to be 4 feet, what length would be necessary to make that? Should be pretty quick. You can do that on your calculator, compare the answer to somebody next to you. If you set up an integral here from 0 to 4, what are you actually finding? You didn't mean area. So if you set up something like this, what are you finding? So you are setting up triangles from 0 to 4 to find the length of the curve, right? So that would be like if this is the origin here and this is 0, that would say go over to the x value of 4. Are you finding what you think you're finding? Talk again at your table. My question was how long should the steel be to bend it to end up with 4 feet? Maybe? So there are two things being said, okay? So two things are being said. So some people are making an upper limit for, some people are solving to get an upper limit. Let's do a simpler example. Let's do a simpler example. So I'm gonna give a function here that is very easy. So draw this with me. Y equals 3x. And suppose I'd like to know the length of the curve from 1 to 4. Okay. So you should be able to get that answer just even thinking about Pythagorean theorem, right? That triangle. So I guess the question then really is this: what integral would give the same answer? So first, what is this hypotenuse? So if that's 3, what's this? 9. What's this? Oh, it's L. Okay, what is it? 3 root 10? So what integral would give an answer? Like the answer to this integral is supposed to be a length, so what integral would give an answer of 3 root 10? If you can answer that, then you should be able to look back here at the question. And again, like, as we think about what we're trying to solve, I've lost the page. What have I done? There it is. So should we be trying to solve this, or should we be trying to solve this? So are we solving something like this, or are we solving something like this? So if you can answer this question, then you should know. So try to answer this one. That's not what I'm saying. So if that's what you're interpreting, so let me rephrase. So when you're looking at this question, so like if I'm trying to find the length of the curve of this simple function from 1 to 4, it should be this integral. We're okay with that? Like, so it's the root, it's 1 plus the derivative of 3x is 3, square that, it's from 1 to 4. And so if we find the antiderivative, it's this. If we substitute, it's this. And that's the same answer that, Richard, you told us from Pythagorean theorem a minute ago, right? So this setup is giving the correct length of the curve is my point. So when I was drawing this, I'm not saying that, so let me draw it just as a sine wave here. I'm not saying I'm telling you it's 4 feet of metal and then asking you the length of the curve. That's not what I'm saying. I'm saying that I have some length of curve or of metal that's longer than 4, and I start bending it. And I'm bending it starting here, and I'm following a form, and I bend it, and I bend it, and I bend it. And when I'm done, I finish with 4 units away. So the question I was asking is how much metal did we start with? So is that the integral from 0 to 4, or is that the integral equal to 4? So that's the integral from 0 to 4. Okay? I don't know. So what is the other one then finding? So if we do this calculation, so the integral from 0 to x of the function equal to 4, how would you say that in words? Because this is also a legitimate question that could be asked. How wide is like the sheet of metal if the length of the curve is 4 is yes. So if I would like think I have 4 units, and so if 4 stops here, I'm sorry, if 4 stops this distance, this pink distance, if that's 4 units long, then this equation would find the x that causes that to happen. Okay? All right, so that is length of a curve. That took too long, but 11.1. Moving on. Well, I just heard 2 things, and then I made a comment, and then people hear the comment and assume that it was always directed to them, and then it kind of spiraled out of control. So what I have here is review of stuff that we've said already. Now, when we talked about this before, like let me zoom out a little bit there and make that look better. When we talked about parametrics before, which is really where we're back here in 11.1, talking about parametric functions and their derivatives, and we're going to talk here in a second about the length of a parametric curve. So I'm mostly trying to remind you of this, that we've already taken the derivative and the second derivative of parametrics. It was actually on your first test. Okay, so the thing to remember about parametrics, so just a quick review, remember that these are functions of x. I'm sorry, functions of t. X and y are functions of t. So they might be something like this, where we'd say like maybe even x of t and y of t, something like that. And so when we try to find the derivative, so if I graph this, remember that they're graphed still on the xy plane, right? We would draw the graph and then the direction would be given by like a little arrow on the graph. So when we find the derivative, we are actually still finding dy dx. And so this is implicit. You could also think chain rule, right? Right here, we could easily get dx dt. Here we could get dy dt. If you want to know what dy dx is, shouldn't I just divide those two pieces? And so we've seen that before, and that's what I have here. Now, when we think about the second derivative, notice it's actually also just implicit or chain rule. You could have that thought. Like if we write this notationally, remember what that's saying is, like, you don't have to write this down, just look at my screen so you don't miss this comment. And then I'll give you a second. Like, second derivative should be take the derivative of the first derivative, y prime, right? Now, when you look at y prime, like, isn't that functions of t, isn't really y prime dy dt over dx dt? Like when we're thinking about what that is then saying, dy dx. So now, if I'm trying to take the derivative of that, that's where this extra chain rule is coming. Remember that we would actually multiply by like a dt dx, and we were like, okay, wait, that's really division. So that is what this is starting to say, but we actually worked this out a little bit further with a quotient rule there, if you remember that. So you definitely are still responsible to know the first and the second derivative of some kind of parametric, okay? You already have some other notes on that as well, so I'm not going to spend too long on it, but you've seen both of these. This piece, you'd go back here, you're taking the derivative, you'd have a quotient, and go. So what I'm more interested in doing is showing how this is related to the length of the curve that we just talked about. Now, when we think about parametrics, think about that we're still talking about like some x and some y, right? So it's a function that tells me the location based upon really maybe like time. So when time equals 1 second, maybe the x value is 3 and the y value is 4, right? That's really what we have here is this function. So that means really then this, if I'm wanting to find the length of a parametric, it shouldn't really look much different, right? If the primary difference is this, that the x distance is some function, isn't it? Like this could be like, again, like a cosine function or a sine function. The y distance could be something like that as well, which means when I start thinking about the hypotenuse, it's still going to be Pythagorean theorem, except there's not going to be a constant here when we rearrange it. So here it is. Here's the length of a parametric curve. Notice it's still Pythagorean theorem, but it's just the derivatives of x and y, since they're functions of t. Definitely want to jot that down somewhere to have that. So it's a pretty small extension from what we just looked at. So I think what I want to do is let's maybe do an example here of the first derivative, the second derivative, and the length of the curve maybe all combined, okay? And I would probably suggest, like, I don't memorize the formulas for the first derivative and second derivative parametrics. It is not worth it. You should really just be able to do chain rule or implicit differentiation and get the answer. So I'm going to flip off of the formula. Everybody have it for the length of the curve. Again, like, if you remember that they're both functions of t, isn't, again, this really the Pythagorean theorem again? Like, so this isn't really much different than what we've already saw. So here we go. Oh, John, are you all right? Okay. So here's parametric. Okay. Oh, actually, already wrote dx dt and dy dt, but I don't think I gave much away because I hope you knew that. If you didn't know that, boy, I think it's over. Now, so if I wanted to know what dy dx was, again, this is the same work that we've done multiple times. Like, we just really need to think about how the fractions can be rearranged. I hope you could write down that answer with hardly any work. What is dy dx? Anybody? What is it? I heard, I think, two things, but I heard bottom function over the top function. Is this what you meant? Okay, so dy dt, and that's what I had on the other screen, wasn't it? That dy dt over dx dt. Couldn't we think about multiplying by dt dx, and the dt's cancel, so this is dy dx. Okay, so there is the first derivative. Okay, so second derivative. So the second derivative of this, so take the derivative of the derivative, and that's this notation that I wrote, like take the derivative of the derivative, right? That's what we're trying to do. So important caution right here, we're taking the derivative with respect to x, but there's going to be t stuff I write down. Chain rule, right? Implicit differentiation, whichever one you want to think, same thing. So we need to take the derivative with respect to x of this. So again, I'm not thinking of the formula, I'm just writing down what the symbols are telling me to do. Can you finish that? Okay, time's up. Let's see how we did. Anybody have an answer? Okay. So first, we have the first derivative, no issues with the first derivative, we already had that, right? So now we need to take the derivative of this with respect to x. So all I did here is rewrite the original first derivative that we said that we're okay with. So now I need to take the derivative with respect to x, but these are t's, and there's where that chain rule is going to come in. So really I just need to look here though, like how would I take the derivative of a quotient? Quotient rule. So low, d high, what do I have to have right here now? Right now? Nope, before I finish. I have not finished taking the derivative of the cosine of t. Should I write a dt dx or dx dt? Dt dx, because it's with respect to x, there would be a dt dx there. And minus high d low chain rule dt dx. Which means I have right now, unless I made a simple arithmetic mistake, that. Anything you want to ask me there? Low squared, I didn't say that. You definitely could and probably should, okay? So in fact, I'm going to factor it out, but instead of multiplying by, maybe I just point something out here real quick. So if I factor this out, and that would be multiplying by dt dx, right? I could write dt dx times everything else there that's left. But wouldn't that be the same as dividing by dx dt, right? Like taking all of the pieces here that are left, oops. So I would have this, I'd have this, and I have this. If I put all of that in the numerator there, that would be the answer. Now dx dt, we actually know, I gave it to you, it's here, right? You could substitute that back in. But I want you to notice something. Now, so you can simplify that a little bit because notice you're going to get a 1 minus sine of t cubed when you're done. The quantity cubed, right? Because you're going to get another one, right? We had 2 from the quotient rule and we're going to divide by another one. So we're going to get that cubed. But do you notice that all of the yellow parts are really just the derivative here with respect to what? Try again. With respect to t, right? So if the question was, if I gave you this in blue and said, what's the derivative with respect to t, we wouldn't write this and we wouldn't write this, but everything else would still be there, right? And that's why we could write it this way. Now, this isn't really the answer to the question, but this is where the formula is coming from. So the formula would say, take the derivative with respect to t of the first derivative. So what if I even just wrote, instead of this, which is what we just had, what if I wrote dy dx? Since dy dx has t's in it, we're going to take the derivative with respect to t. So pretend that there is no x here involved with it, except it's really just been factored out and then divided. So that's where this formula then is coming from. Now, that's not the answer to the question. You need to simplify a little bit to get the answer to the question, but I hope you can do the algebra to do it. So then this would equal, what did we just find? The second derivative. Okay, and that's what I mean, that you don't really need the formula. You can remember the formula and it might make it quicker, but if you don't know the formula, like I think this one messed some of you up just with the trig functions and trying to simplify that and make that nice, but you could just take the derivative. You just have to remember the chain rule. Okay? All right. Siri, is that what you want? You could. So if you want to simplify this, if you're looking for the answer here, so you could distribute this. You can square this. So we're going to have negative sine of t plus the sine squared of t minus a cosine, no, plus a cosine squared of t over 1 minus sine of t cubed. And this is 1, so there's the answer. I didn't hear you, Siri. It is, yes. And so notice that all of this final answer, the best thing then to write, do you notice that that's actually this factor? So there's your second derivative. Everybody get it right? Good. Did I just lose you? Wait, so this is 1, it's not 0. So if this is 1, and you think about then what's left, do you notice that this is a common factor? Right, because it's negative sine of t plus 1, that's what this is, negative sine of t plus 1. This is to the first power, second power, that's where we finish. Where's the negative sine of t? That's... I just distributed. Is that where you're looking? This piece here? So just distributing here. So there's your second derivative. A lot of algebra there. Okay, let's look at here as we kind of wrap up today with section 1. I want to look at, we're going to talk about vectors here in the next section. So that portion of the question we're not really going to try to answer. It's a direction and magnitude, yes. We'll talk about what this is. I'm wondering if you can answer part B. I think you can do part B. Should try that. Time's up. Let's see how we did. So they are giving a huge hint here. Even if you know very, very little about vectors, you can answer this question. So notice it says that in the xy plane, it has a position of x of t, y of t. That looks parametric really then, doesn't it? And so as we're thinking about then the vector, like it really is this connection back to parametrics. But anyway, so x of t, y of t. But then it turns around and says it has a velocity vector of this. So my question is, looking at this and understanding what you know about velocity, what's the connection between velocity and position? Velocity is the derivative. So if the position was x of t, what is this? What is this? It's dx dt. It's sitting right there. If you didn't do that, 30 seconds, your answer should be less than 1. That sounds right. 3 decimal places, so 3. Be sure you're in radians. I don't know. Okay, so this is really just the first derivative, right? That's not connected to asking the second derivative question because they're not asking it here. But really, the key is that the derivative of position is velocity. So if the position, if the velocity vector is really the derivative of those two pieces, we're just going to divide those two things, except they're telling us that the rate is 2, so then we're going to set that equal to 2 and solve. That's it. So there's your slope, setting equal to 2. I'm going to guess that most people there, like, what do you think the most common wrong answer for B would do? Okay, let's say you recognized that these were the derivative, because you're probably going to do that better now. What's the next biggest pitfall you think? Substitute 2 in for t, yes, but like, so this doesn't say the time is 2, right? It's asking for the time and telling you what the slope is. A lot of people just substitute the value in. They're like, well, there's a 2 and there's a something I don't know. I guess that's it. And so be sure that you think about that. Okay. Okay. Which of these questions, going back here, is the length of a parametric curve? D is. Now, when you think about, again, what we're given, I have a position, which, again, that means that this cosine of t squared must be x prime of t, or dx dt, right? This is dy dt. Could you set up an integral? Just set up an integral here for me. Let's not finish it, but set up the integral that would give the distance from t equals 0 traveled for t equals 0 to t equals 1. You answered the wrong question. But we're going to have to think about how that could be different here for parametric. So I think I want to have that maybe another time. So I have a graph here. It says at time t, the position of a particle is given by x of t, y of t, where dx dt is this. The graph of y is this. Do you notice that they actually just made this like a multi-step process to figure out dy dt? Sitvika? Well, if it's not parametric, use the other one, right? If it's a you could, it will, but it's usually difficult to turn it back into dy dx because it's really just that piece factored out. So it should give you the same answer. Be careful that your limits though are in terms of x and not t. Is that maybe what went wrong? Okay. So can we answer A, B, and D? Okay, well. We haven't really talked about C, so I think you can answer A, B, and D. Try it. Skip A, just do B and D. Fundamental theorem of calculus. Here's the answer to B on the screen. So we just need to figure out y prime of 3 and divide it by x prime of 3. Right? Wouldn't that be the derivative at 3? So let's go back. So stop. So find the slope of the line tangent to the path of the particle at t equals 3. So we need to find dy dt, divide by dx dt, and then make t 3. So dx dt is given to us. Dy dt, we have to go back here and go to 3 and figure out the slope. So there's the answer. I don't know why they don't show 3 decimal places. They should have. Is it 0? Sometimes they tend to show it and sometimes they don't. I don't know. Questions on B? Okay, then D, find the total distance traveled from 0 to 2. Well, again, this really looks like parametric length of a curve because I have a function for x and y in terms of t. So solving it, there's the answer on the screen. Why is it more than one integral? Because what, John? Yeah, so y changes, this function changes. So don't I need to break it apart where there's different functions and different slopes? So that's what we have. If you didn't think about that, that's definitely going to be an issue. So there's your 2 integrals. There's your answer. So Vika, did you have a question? It kind of looks like distance formula, but remember it's really Pythagorean theorem, right? But Pythagorean theorem and distance formula are really the same as well, which is why it looks like that. So this is that length of the hypotenuse is really what we're doing here, okay? But you're right to notice it kind of looks like distance formula because it is. So let's go ahead and do A, and we're just going to do A here together, okay? So it says find the position of the particle at t equals 3. Find the position of the particle at t equals 3. Now, when we think about position, we should be thinking about like some ordered pair is really what we want to know, right? So if I think about a parametric function, like when we first talked about these, I kind of talked about it like I'm going to choose t values, we're going to find the x and find the y, and I end up then with a point I'm plotting here. So when it says find the position of the particle at 3, it's basically needing us to find x of 3 and y of 3 and say that what that then is. That would be the position of the particle. How far over is it? So again, this is the graph here of t and y. If I would graph x and y, where's the ordered pair where 3 seconds would correspond? That's what this question is asking. Now the y is actually pretty simple. So what's y of 3? It's a half, right? It's this point right here, okay? So that part is easy. The other part, I need to do a little bit of work. Now they're telling me that this is dx dt. So I'm definitely going to need to integrate, right? I'm going to have to integrate this to go backwards to figure out what x is. But how does this initial position play into it? Like what I'm wanting you to kind of remember is this statement. Do you remember that when we thought about, I'm going to go over here for an aside, I'm going to go back and give you a second to see if you can finish it, and that's where we're done today. When we thought about the fundamental theorem of calculus, because that's really what this question is, it was antiderivative upper limit minus antiderivative of lower limit. And then we rearrange this to try to write the antiderivative. And so the antiderivative really must be the integral from a to b of the function plus the antiderivative at a. And so we had conversations about like how there's always a match between these two pieces, right? Like we would set up integrals, like we would have an integral from a to x to get this antiderivative for some function. We would have called this t. And this piece over here should still be the antiderivative at a. And so if I wanted to integrate from 3 to x, then I would have had to have over here like that capital F of 3, right? There was always that matching between those. So somehow this question is really like that I have a dx dt. Now I can't just find that antiderivative because wouldn't there really be some constant I don't understand? That's really connected to that capital F of a. So how does at t equals 0, the position is 5, 1. So somehow those pieces, I need to write x of t is equal to some integral. You need to put something here, something dt plus something. So what are you going to put in all of those blanks with this information that then would be true with what you understand about the fundamental theorem? Talk at your table, see if somebody can do it. Okay, lower limit, what is it? So lower limit, I hear a vote for 0. I heard a vote for x. 0? Why 0? It's actually this starting value, which means you better already know what number goes in that box. Is it 5? Nene's asking. Why is it 5? Why isn't it 1? Okay, so if I understood you, you actually are implying what the upper limit is right now, that the upper limit is actually t. So if t happens to be 0, this integral would drop out, And what is the x value supposed to be at 0? Doesn't this say it's 5? So the constant has to then be 5, and that means this piece should be that derivative dx dt. Like it should be that function sitting right there. So this goes here. Now, so when this is saying find the position of the particle at t equals 3, well, I could put a 3 in now for t, couldn't I? So this becomes the integral from 0 to 3 of my dx dt. And so it's really just this. Don't let the notation or the number of dt's there bother you. Add this 5. Type that in your calculator. I have the answer here somewhere below. So remember, you're only finding the x value there, which is, College Board says it's that. Anybody do it? Okay. Yeah, so we just need enough here. Like, I would say that, like, I think they're just trying to show what this integral is. I would have typed it in all in one step to get this answer. So you're right. There is a loss of precision here, but they're showing that. So if you would do this separately and think about adding that first piece to it, definitely be careful about rounding this before you add, right? Like that could be a. I would definitely do it in one step as well. And so final answer is the ordered pair because we got to use the y value too. So on the calculator portion, you can always give a decimal. And if your calculator spits out an exact answer, you could just write down the exact answer, that's fine. On the no calculator, remember you don't have to simplify. So if you get something set up that's the right answer, just stop and go on. I wouldn't even bother because that means you're going to now probably have done something that caused an error. So you shouldn't even be trying to get a fraction or a decimal on the no calculator portion. Sorry. Yeah, like I like that thought that remember that the integral is the net change. So this is the change in x basically that we're finding here, right? So if we integrate from 0 to 3, it's the change in the x distance from 0 to 3 seconds. But where did we start? We started at 5. So 5 plus that would be the final answer. Okay? Yeah, so if the fundamental theorem like bothers you in setting that up, like then yeah, you can definitely think, remember the integral is only the net change. Don't forget about where it started. Okay? So do you want to try this one on your own? So this is the one that we skipped. So this should be part A here. That is like what we just talked about. And then we're done. Use your calculator, spit out a decimal for it. You have an answer? You ready? Just yes, coordinate. Net change plus where we started, 2.557. So, parametrics. So this is the whole lesson on parametrics. I'm not really looking any more at them. We'll talk about vectors, we'll talk about speed and how that connects maybe to this parametric thought, I guess. I haven't really done that, but we'll do that another day. So this is really 11.1 and 8.4. I'm going to add a MyMathLab for both of those. See you tomorrow.